Good afternoon and welcome to our webinar on neural networks, teaching your treatment plants to be smarter. My name is Ruth Clark and I'm a business development manager within the advanced infrastructure analytics team within Xylem. And I'm going to provide an introduction to this webinar and then hand over to my colleague, Jörg Gebhardt, who will then talk us through the detail of the treatment plant optimization. So firstly, who are Xylem? Well, Xylem was spun off from ITT in 2011, a company that has been involved in the water industry for over a century. Xylem's probably best known within the water industry for flight pumps, and amongst the audience today, they probably also know Xylem for many treatment products such as flight mixers or sanitaire blowers. Over the last 5 years, however, Xylem has become more involved in the decision intelligence technologies and has acquired a number of companies to provide a portfolio of solutions aimed at improving the operation of assets owned and managed by water and wastewater companies. One of these companies that Xylem acquired was Aquatune, a company that Jörg Gebhardt, who will soon be speaking, was founder and managing director of. Utilities around the globe are collecting enormous amounts of data, but not necessarily always making as much use of it as they could. Our decision intelligence solutions are aimed at making use of this data in order to enable utilities to operate their systems more efficiently and, where possible, to draw insights and predictions from that data. These tools allow utilities to move more easily from reactive mode to predictive mode. So why is there a need for these decision intelligence solutions? Currently, particularly within the UK water industry, there is a drive to do more with less. So that's to reduce leakage or reduce pollution incidents, but also to reduce costs. And optimising the operation of treatment works is one key area where energy and chemical consumption can be reduced substantially. This webinar explains Xylem's approach to helping utilities understand their plant operation and how they can learn to operate it more efficiently, while still meeting or indeed improving the quality requirements of the effluent. I'm quite sure that you will have many questions during this webinar, and rather than disturb the webinar, we will have time at the end of the session for these questions. So please do ask questions via the chat box during the webinar, and we will make a note of these, and if there's time, we'll ask Jörg at the end to be able to shed some light on the questions. If time is limited, then what will happen is I will collate those questions that we don't have time to answer and disseminate the responses afterwards. So I'll now hand over to Jörg, who will talk us through the process.
Yes, thank you, Ruth. My name is Jörg Gebhardt. I'm from Germany. I studied physics in Cologne, and after that I worked in different industrial companies doing automation and SCADA systems. And my last position before I founded the company Aquatune was with a company called Passavant, which belonged to Biffinger Berger, and there I did automation and SCADA systems for the wastewater area, and that's when I discovered that there is a need for some support, because the operation of a wastewater treatment plant is quite a challenging task. It's more challenging than, for example, to operate some chemical plants, because there you have one point of optimum operation, and once you found that, everything is fine. But in wastewater treatment plants, at least in municipal wastewater treatment plants, you have the challenges that come with dry weather and stormy weather conditions and strong changes in operating points. And so I saw that there was some need, and we came up with the idea to use artificial intelligence for this. We started this in the year 2005, and at that point nobody was talking about AI or artificial neural networks, so that was kind of crazy. Me and my colleagues visiting wastewater treatment plants and talking about artificial neural networks. But as it turned out, it's quite a useful tool that helps to meet the challenge of operation, and so we grew and were successful. Here in Germany, we have about 30 to 40 running plants, not only in wastewater, but also in clean water applications or in biogas. But I will focus here on wastewater, and maybe at the end I'll talk a little bit about drinking water applications. So since the beginning of the year, we belong to Xylem. So we are a Xylem brand, and everything runs under the label BLU-X, which is our label for this kind of smart solutions. And yeah, let's talk about this. Our objectives are the optimization of energy consumption and chemical usage in the plants, while increasing compliance margins, because at least in Germany that's so, and I guess in the UK it's pretty much the same, that first priority is meeting the legal limits and complying to the limits. So that's first priority, and after that we want to do optimum use of energy. We do not want to increase our carbon footprint, and only use as much chemicals as is needed. First, I would like to start off the talk with a picture that shows something about the efficiency of our process. I'm talking about activated sludge plants. That's activated sludge process is something where the biomass is doing the work, and for the work it needs some oxygen. And to give you some figures about the efficiency of that process, I came up with that picture. From the left side, we see the air or the oxygen coming into the plant. The figures that you see here, the 27 tons of oxygen, correspond to a plant in Germany. It's Hamburg-Dradenau, which is a huge plant. It's got a capacity of 2 million people equivalents. So it's the best, or the most efficient plant that we know up to now. So we have 27 tons of oxygen being supplied each hour into the reactor, and one fraction of this goes into the biodegradation of the chemical oxygen demand, in that case 6.7 tons of oxygen. And then we have very, very little of the oxygen going into the surplus oxygen. So this is 172 kilograms, which is really tiny compared to the other figures here. And that corresponds to 2 milligrams per liter concentration multiplied by the reactor size, which is huge in that case. But it's only 172 kilograms, and all the rest goes into the atmosphere and is lost. So all this precious oxygen that you produced by applying a lot of energy and producing a lot of carbon, which is, as we all know, greenhouse gas. This shows that the process is really not very efficient, that most of the oxygen that we are producing is lost in the process. So it is worthwhile to think about how can we improve the efficiency, how can we reduce the losses. That's the one message of this picture, and the other message is that the most common way to do it, to control or to operate a wastewater treatment plant, is to control this, the parameter surplus oxygen, the dissolved oxygen. And by controlling this parameter, everything else will swing up and down, including at least from our point of view, the most important parameter, which is the specific energy per load. This is something that will be floating around, and at times it will be as low as 0.3 kilowatt hours per kilogram load, and sometimes it will go up to 5 or 10 kilowatt hours. So there's a huge spread, and that's the result of applying control of the surplus oxygen, a parameter which really is not very significant. It doesn't tell you much about the state of the process, because it's just the difference of two very big figures. The one is the oxygen quantity that you supply to the process, and the other one is the consumption or the losses. And so I think that surplus oxygen control is done because it's easy, it's reliable, it's cheap, the sensors are available for little money, and if you do it like this, you can be sure that the nitrification will be done nearly completely. But it's not the method to apply if you want to have optimum performance, if you want to control your specific energy consumption and do it with the least possible quantity of energy effort. So what we do is we try to estimate the load that's coming into the plant, and the load is composed of chemical oxygen demand or biological oxygen demand plus ammonium, because it's carbon and it's nitrogen, which is relevant to the aeration, and so it's relevant to the energy consumption of the plant. And then we want to derive from this how much oxygen is needed in the process and run it the most efficient way. As I said, we use methods of artificial intelligence. How can they help us? Well, we try to simulate the process that's going on in the reactors, and we want to control this urban water and wastewater system to improve the environment while saving ratepayers' money in this way. And we do it by having advanced sensing. So we need sensors. The data is the eyes and the ears of the system. So the system is relying on data, and I come back to this later on because that's very important. It's very important to have reliable data, and as we all know, the data from the real world are always uncertain. They have problems, there are gaps, interruptions, and so on, and we have to deal with this. This is very important if you want to use a data-driven optimization system. Once we get the data, we can learn from it. We apply machine learning. That's much cheaper to let a machine learn than to have some highly educated people spending a lot of time on coming up with models. So we come up with a digital twin of the real world by learning, and ideally the digital twin would behave nearly exactly as the real process behaves. And once you get that, you can use it to come up with a dynamic control system. Now the system is basically a 3-tier system, and the first tier is what we call turn on the lights. So that means we collect the data, we can generate real-time alerts, we have full SCADA integration. That means we can connect to whatever the existing SCADA system is. We have solutions to connect to nearly everything that has an interface to transmit data. Then we can, when we get the data, we create the digital copy or digital twin, and we would start off with data from, let's say, 12 months, because then we can cover all seasons like spring, summer, autumn, and winter, so that we get the different conditions and that your process is running. And because the system can be retrained and it can learn new situations, it will become better and better with time. And once we get the copy, we can have an optimization strategy on top of it. So the digital copy, it's like in your navigation system in the car. This consists of two modules. The one is the model, which is in that case it's a map of the roads, and the system needs some map. So in our case, this is the model, And then we have an optimization algorithm. In the navigation system, you have an optimization strategy that gives you the shortest path from A to B, or the fastest connection. And that's the same here. The models don't care what you want to do with your plant. They just show us the exact behavior of the process. In our case, it's the carbon, nitrogen, and phosphorus elimination process in the activated sludge tank. And the optimization strategy is where you formulate your targets. So the targets could be to run at the lowest energy level that is possible, or it could also be to run at the highest elimination rate that is possible, or something in between. That's the question, how you formulate your target function that we are running on, and how you want to drive things. Now let's come to the digital copy. As I said, we generate it by using machine learning. So the advantage is that the machine does the work. But we have, of course, we have to prepare the data. That's a lot of labor. But once we got a clean database, the neural networks are able to learn the interconnections of the different parameters. And then we have to test whether the models are any good. So we call that process the validation. That's also been done if you have conventional models. You also have to do a validation to make sure how precise is my model. And as you can see here, you have a green curve, which is a measured curve. That means that's the reality, or at least it's close to reality. As a physicist, I have to tell you that something like reality does not really exist, but I don't want to confuse you. It's just the green one is a measured curve, and the blue one is the model curve. And you see that they are not perfectly aligned. Sometimes the green line is above the blue one, so we have an underestimation, and sometimes it's the other way around. But on the average, it gives us the trends, the changing of the target value, which in this case is the elimination quote of chemical oxygen demand. So we test the quality of our models before we use them. Now, how does this look? This is a simple picture. It's not a picture. It does not show the signals as they go in a real production system. It's just the principle. For didactical reasons, I took the raw signals here, like influent quantity, temperature, loads, total solids, aeration intensity, and so on. In a real production model, we do not use the raw signals, but we prepare them. For example, we do not apply the influent quantity or some incoming concentration to the system, but from the flow and the concentration, we calculate the loads, like for example, kilograms of ammonium per hour, and then we divide this quantity by the dry solids, which corresponds to the quantity of the available biomass that I have in the reactor, and by this I come up with a quantity we call the sludge loading, and this is the quantity which is physically active in the process, and this goes into the model. Or another example could be the flow. We do not use the flow itself, but we use the hydraulic retention time. So this has the advantage, it's the directly effective physical quantity, and you can compare it with other plants, even if those other plants are of completely different size. You get comparable signals, and we can check whether the figures or the data are in the expected range or are not, and if not, then we will look for the errors, because, for example, it's a difference whether you measure your flow in cubic meter per hour or liters per second, or I think you have something like gallons. We don't know that, but it could give you different figures. So we have to check for this, that all the figures and the physical dimensions are correct. And then the artificial neural network, which is symbolized by the blue neurons here, which are interconnected with synaptic connections here. And don't let you be confused by all those terms. It sounds a little bit like science fiction, but it's just pure mathematics. It's applied mathematics, what we are doing here. And if the system is trained in a proper way, it will map the input values to output values, like degradation rates or effluent concentrations or energy consumption or whatever it is that is of interest to us. So it maps causes to effects, or let's put it in another way, it is a kind of pattern recognition system, because all the numbers that you have here at the input layer, they build up a pattern, and the artificial neural network will recognize that pattern and will memorize the target values. So that's what the system is. In fact, it's a pattern recognition system. And that means that all the information that's that's contained in those input signals will help us to identify in which state the process is and what elimination rate of carbon, ammonium, nitrate, phosphorus we can expect. So that's the way it works. Here again is a validation curve, and this time we have a correlation graph that shows us a green line is the ideal model, which of course does not exist yet. We are working on it hard, but we still have to deal with uncertainties, and that's natural because all those measurements have their uncertainties, and yeah, we have to deal with it. And you can see that the model results are sometimes overestimating and sometimes underestimating. But anyway, they are useful, so we can come up with alerts for the customer. So we can, in that screen, you'll see a system we did for Nuremberg, where we have a monitoring system. The customer was aware of the fact that all his online sensors had some kinds of problems, and they're all not available all the time, but they have to operate the plant all the time. So they wished some substitutions for the physical sensors, and we came up with soft sensors, which also work with artificial neural networks and give up some virtual measurements. And here you can see in the different diagrams, you see the blue model results compared to the measured signals. And this has the advantage that when your sensors have to be calibrated and are not available, you still receive some signals that you can use to operate the plant with. Now, this picture is meant to show how model-based optimization works. You have some kind of real plant, and it doesn't really matter whether it's a wastewater treatment plant or drinking water or an energy plant or biogas or whatsoever. It's a plant, and from the left there is something going into the process, and on the right there's something going out of the process. And some of the incoming signals are signals that you can manipulate. So like, for example, you can adjust the set points of the aeration or the recirculation quantity or precipitants or flocculant dosages and so on. That's where you do your decisions in the operation of the plant. And if you do good decisions, then you will reach your targets, like effluent qualities. You want to keep your nitrogen or phosphorus concentrations low, and So you can do this, but it's challenging, as I said, because all the parameters are moving up and down all the time, especially when you have transitions from dry weather to stormy weather conditions and so on. And whatever you do to the process, it will take a while till the results show up in the effluent. We call this dead time or lag times, and the control engineers hate it because it's very hard to control. A simple PID controller won't be capable to do that task. So the idea came up to support this task by the application of simulation. In our case, it's artificial neural networks. It could also be some kind of first principle based models, like, for example, ASM models, activated sludge models, which consist of systems of nonlinear partial differential equations. That does not only sound very complex, it's hard to do. It's a big effort to do this. We are trying to do this since '85. I think that was the time when Professor Guya came up with the ASM1, the grandfather of all those models, and it takes a lot of effort and labor, and yeah, you always have to adjust it because models and reality always have the tendency to split and to travel away from each other. And in the case of differential equations, you would have to recalibrate it, which is another big effort. And we have the advantage that with our artificial neural networks, it's just a machine training that we do. We just take the most current data sets that we collected, do a retraining, and then the model is up to date again. And the idea is that the model can give you predictions at once. You don't have to wait for hours till the results show up in the effluent, but you just look at the results from the network. You get your answers at once, and so we can avoid the problems with feedback, because in feedback you always have to wait and you come too late with your optimization strategies. We do feed forward. That means through the help of the simulation, we look a little bit into the future, and then we can react to the future results and bypass the feedback times. So that's the way how it works, and then we use something like this control circle to guide the process. That means the optimizer. Oh, I'm sorry, that's still a German term, so I have to apologize for this. The green box, that's the optimizer in our case. And there is another science fiction term called genetic algorithms that we use. We use that because the space of the possible solutions is huge, and it would take an awful long time to use conventional search algorithms. So we use genetic algorithms, but I won't go into the details here. It's just the idea is that the genetic optimizer plays around with those manipulable variables like aeration intensity and recirculation intensity, applies this to the models. The models give him the targets, which is the black box Zielgrößen. That's the targets. And then he will try to come up with the best solution. And at the same time, he will watch for all the constraints that it has to take into account. Like, for example, the most important constraints are the allowed effluent concentrations. And he's not allowed to break the limits. But on the other hand, he also has to comply to limiting conditions of the plant itself. As for example, if the optimizer comes up with a proposal, please apply 5,000 cubic meters of air per hour, but your blowers are only capable of supplying 3,000 cubic meters. In that case, the proposal would not be very helpful. So we just don't let him go into that area. We restrict the optimizer to the area of physically meaningful and helpful proposals, and all the others will be omitted. In the system, we have a logic that tries to detect whether your plant is under normal conditions, like for example dry weather conditions when you have no problems to comply to the legal limits, or whether you have some stormy weather conditions. In that case, we would switch our traffic sign from green to red, and then switch over from a saving strategy to a load strategy. In a saving strategy, we would try to run the plant in the most economical way, and in the load strategy, we would not care for the energy or for chemicals. We would just try to prevent, as far as possible, to prevent breaking of legal limits. And most people are not aware of it, but all our wastewater treatment plants regularly go into overload, which means you have more kilograms of load, like carbon and nitrogen load per hour coming into the plant than your maximum elimination rate is. And then as a consequence, all the concentrations are rising. And in that case, you need some support. And it's also very important in that case of a storm event to find out which parameter is the most critical parameter, because then you can use your resources to reduce exactly the most critical parameter. Like for example, in the beginning of the event, usually you need nitrification, so you will activate all your aeration zones and try to do maximum nitrification to capture the ammonium concentrations. But at a certain point in time, the situation will change, and your ammonium might be at a high level, but it's stabilized. It doesn't approach its legal limit anymore, but you are producing a lot of nitrate, and your nitrate values, or your total nitrogen value, is approaching its legal limit. And in that case, it's better to turn off the aeration and switch off swing zones to get more denitrification capacity, because you need it desperately to reduce your nitrate. And what we very often see is that in the case of rain events, people are increasing the aeration, but then they don't switch off. They just keep on pushing the aeration. They reduce their ammonium concentrations, but nitrate concentration goes through the ceiling. So the system can do that very efficiently, because the system can watch all parameters, and it will always check which parameter is the most critical, and then correspondingly change the use of the resources, because you have your resources only once. You can, and you have to make up your mind whether you want to use it for nitrification or for denitrification. And by this, what we do is we control very efficiently the most important parameter. It's a key performance indicator. It's specific energy, which means kilowatt hours per kilogram load. What you can see here is data from a German plant. It's a North German plant. And we have data here in the upper diagram from the time before we started the optimization, and the blue line shows you the value of the specific energy, and you can see it's somewhere on the average, it's somewhere between 0 and 1 kilowatt hours per kilogram, but it can go up as high as 5. So if I was the manager of a plant, I would ask my operator, hey, when you're able to operate the plant at 0.4, why did we use 5 last night? Because that's very expensive, and it doesn't only drive your bill of electricity, it's also bad, for example, if for the denitrification, if you apply too much oxygen. So after optimization, you can see it's not a perfect line. It's still swinging up and down, but all those extreme variations are reduced completely. That's where those, as you can see in the upper diagram, the red areas, those peaks have gone, and those peaks are driving your bill. So the peaks are gone, and the mean value of this came down. In that case, in that special case, in this North German wastewater treatment plant, it came down by an amount of 26.7%. If you take into consideration an energy reduction of 26% for a wastewater treatment plant of 600,000 or 700,000 people equivalents, that's a lot of money that you save per year, and the return on investment in such a case is significantly below 1 year. So it's very worthwhile to think about this kind of operating optimization system. Now, the results that our optimizer calculates in the form of predictions and proposals for you to adjust your set points can be communicated via graphical interfaces. This is just one example of such an interface. I think that's the city of Cologne, where you have the incoming values here, and then you have the different activated sludge lanes. They have 14 lanes. Each lane has 5 cascades. So that's 5 times 14 cascades that they have to operate. And for each cascade, they have to make a decision about the aeration intensity. And then we have all the recirculations and return sludge and so on. And that's where we have some proposals, and in the top right, the red boxes are the predictions from the models, and the yellow boxes are the measured values. And this is just an example. This can be adjusted to your needs, because the best thing is to just integrate it into the existing SCADA system in a way that the operators are used to, so they don't have to learn how a new system or new graphical user interface works. Now, to give you an impression how this system works, how does such an optimization strategy work, I just gave you some typical examples of strategies. Like, for example, the most important question if you want to optimize something is which parameter is limiting the success. For example, is it oxygen? Then you have to increase the aeration intensity. But if it's the retention time, then you have to increase your aeration volume if you can. Or is it the nutrients? Like, for example, in the case of anaerobic treatment systems, you have to feed some nitrogen and phosphorus to support the chemical oxygen demand elimination. Well, if there's a limitation in the nutrients, you have to start the dosing and so on. Or in the case of denitrification, sometimes you have a lack of carbon. In that case, it would be a good idea to do some dosing. But dosing is expensive. If you have to buy methanol, the prices are high. And you don't want to do it if you're not sure that this is really the limiting parameter. So that's the question. And then what we do is apply the same strategies that the operators apply. Like which effluent parameter is more critical, ammonium or nitrate, or which boundary conditions are in force, which loadings are expected. And what we do is exactly what the human operator also does. The only difference is that we do it on another level of precision, because we can use the models that give us predictions, and those predictions help us to have a very precise understanding of what is to be expected if I do this or that. And that's the difference. But it's not a principle difference. In principle, we do the same as you do. It's only a question of precision and of course, also reliability, because the system can do it 24 hours 7 days a week, and it doesn't get tired or something. The only problem that you have to be aware of is Microsoft updates. They can sometimes be disruptive and interrupt your procedure, but we know how to deal with it and can help you. Yeah, we have the case study of Cuxhaven was one example. Oh, 26.3 was the exact number of savings we have realized there. And that was the problem when we started with them. They wanted to reduce their energy consumption for the aeration of 5 parallel biological tanks, but at the same time complying with legal effluent concentrations. And we built models of the carbon, nitrogen, and phosphorus elimination processes. We created an optimization strategy, and we continuously calculate the best set points for their aerators for each zone. And they didn't have the life sensors we needed. As I told you, that we work based on the estimations of load that are coming into the plant. So we want to know the nitrogen or carbon concentrations in the influent. But if we don't have them, then we have to deal with this, and we do this by applying virtual analysis. That's also an application of artificial neural networks that help us to construct an incoming signal which is very close to what we expect to be there. So this helps us in that case to run the plant. Now, I think I gave you some overview over the application of artificial neural networks in the wastewater treatment plant. Ruth, I hear.
Yes. Can you hear me?
Yes, I can.
Excellent. Thank you very much for that. That was informative as usual. And I'd like to thank everyone for their patience whilst we got the sound issues sorted out at the beginning there. I was going to see if anybody had any questions that they might like to raise for Jörg to answer. Okay. I can't see any that have popped up in the chat box. I don't know if that's another technical issue, but we don't have any coming in yet. So if anyone does have a question they'd like to raise with Jörg, now is the time to do it. If not, I was going to go to a slide with my contact details on, so that people could send them through afterwards, and we could just reply by email from there. So we don't have the slide with my details on. It's
the last slide. Just keep on pushing.
Okay.
I had some drinking water applications here, but that's your.
Oh, okay. Yes. Okay. So unless you want to go through the rest of those slides, Jörg.
As you like.
Or you finished.
If this, we can leave it here, but if somebody is interested in seeing some drinking water applications, because you can apply the same methodology to nearly any technical or biochemical process. And in drinking water areas, we use it to manage the levels of elevated tanks for energy reduction, or we use it to come up with optimum dosing for coagulants in the drinking water treatment, or for leakage detection, and for prediction of consumption behavior and this kind of things. Because artificial neural networks are really good at pattern recognition. As you know, they are also used for face recognition and applications and so on. So they are very powerful tools, and you can generate a lot of benefits. And yeah, that's what I wanted to explain to you or to show you. So if you have any questions, please feel free to ask.
Okay. As I said, I still can't see any on the chat box, and I'm not sure if that's a technical issue. So what I will do now is, if I bring the webinar to a close, anyone who wants to contact us, please do use my email address, which is showing on the screen now. and we'd be more than happy to come back to you with answers to your questions, unfortunately, as we're not being able to see any. So I look forward to hearing from some of you over the coming days with your questions. So thank you very...
Question.
Yeah.
Yeah, is the presentation available?
Yes, well, we can make the presentation available. Also, the webinar's been recorded, so that can be made available also. So yeah, sure. Thank you very much, especially to you, Jörg, for your knowledge sharing there. Yeah, and I look forward. Okay, bye-bye.
Okay, thank you, everybody. Bye-bye.